In the last class, we studied about the twisting behavior of circular shaft. Right? That's the very commonly used shape of shaft. But today, I like to consider different type of cross section. This is also very widely used. Thin walled non-circular shaft. Closed section. So today's topic is thin-walled non-circular shaft, and this is closed section shaft. So thin-walled means the cross section consists of thin wall. This is thin wall, something like that. This is thin wall. So there are many thin-walled beam or shaft. So this is thin wall too. This is very well known wide flange type cross section. This is thin wall. So in engineering, real engineering, we are using thin walled cross section very widely because this thin wall type can reduce the cost of material cost, and the behavior is very effective. And closed means this is closed section, this is open section. Closed section. So today I like to talk about this thin-walled closed section type cross section, and I like to study on the twisting behavior of this cross section. Okay? Maybe you think this could be a very complicated lecture. Let's consider thin-walled cross-section looks like this. This has a general shape. Okay? It looks like a tube. And this shaft have a direction, longitudinal direction, x. And I'm going to give torsional moment mx. And let's define the midline of this cross thin-walled section. And this through this midline, the coordinate system S is defined. Okay? S is coordinate through the midline of thin wall. Okay? And thickness T is a function of T, S. So thickness can be changed. And now let's consider small part of this cross section. So very small part, this part. Okay? And let's say this small part. it has a dimension S, ds, and dx. So let's redraw only that small differential part of the inward cross section. It looks like that. It has length dx from here to here ds. This is a very small part of the cross section. And in this case, this is a pure twisting case. So only two stress and strain is not zero. So in this case, so let tau is a shear stress. So Sx, xs actually is not zero. Actually, both are same, right? So only one shear stress exists. Non-zero shear stress exists. And let's say that stress is tau. Okay? And here, thickness T. And also, thickness also is changing here. Thickness is equal T plus ds dt ds. Thickness is changing, right? Or you can think just this is a T plus delta T, right? Same. And let's consider the stress applied in this small subject. So, due to the definition of transpose shear, in this direction, we have a tau, okay? And in this direction, so we have a 4 tau. This is tau. This is tau 2, and this 2 will be tau plus delta tau, right? So, on the pore surface, transpose stress tau is applied, and let's take the sum of all the pulses in x direction is 0. Then tau plus delta tau and T plus delta T dx. This is stress pulse applied on the top surface, right? Okay. And minus tau T dx equal 0. Okay. Then in the we can delete the dx, right? Then tau t plus tau delta t plus delta g t plus delta tau delta t minus tau t equals 0, right? So here we have the same thing, tau t here and here, right? And this part is much smaller than this, right? Delta t, delta tau is both are very small thing. So this is much smaller than. So finally we have a tau delta t plus delta tau t equals 0, right? And we can think here delta t equal dt ds, right? And delta tau equal ds dt d tau ds, right? Same thing. Let's put this result into here. Then finally we can have tau ds d tau ds dt plus ds d tau t equals 0, right? Then finally we know ds d tau t equals 0. This is the final form. Okay, so in thin world, non-circular closed section case, very important thing is that ds d tau t equals 0. This means t multiplied by tau multiplied by t doesn't change about the line S, right? Cross section. Even though you change the S. And so at all the cross section, okay, here tau t is a constant, right? So actually we are saying Q equal tau t is a constant. We are saying this Q is a shear flow. Shear flow. We have a constant shear flow. Okay, when the twisting moment is applied, constant shear flow, there exists constant shear flow through all the thin wall section. This is a very important thing, and then this will make the problem become easier. So let's consider the arbitrary cross-section again here and here. And let's say this point O is the center of twist. And from here to here is R. And this is a ds. This is midline. Midline. Let's say mid curve. And S. Let's consider this small part. This small part of the section. ds. Then we can calculate the moment mx with the equation r q ds. So q is a shear flow applied at here. This is a q. This is a q. So q is a force, right? Q is a force. This is a force. Q multiply ds is a force, right? And R is a moment arm, right? This is integrate. If I integrate this moment at all the segments of this thin wall, we can calculate the cross-sectional moment, right? This R is a moment arm. Okay, and Q equal tau T. Then this become tau T, because tau T is constant, so it can be outside of integration, R ds, right? Now let's look at this part. Watch this in geometrically. Let's look at the here. Okay. Let's look at this triangle. What's the area of this triangle? 1/2, and base is ds, and height could be r. So r ds. Because ds is very, very small, right? So it means this equation become changed tau T to A. So if I integrate all of this triangle and changing the through the S, we can calculate area of this, right? This area equal A 1/2 R ds. This is the area, right? Area of this closed shape. So this is A and tau T to A. Okay, so here A. Okay, here let's write down here. So because here we have 1/2, I need to multiply 2, calculate this integration. So A equal area enclosed by mid-curve. And finally, tau become 2ta mx. When the geometry of cross section is defined, given, and if we know the total twisting moment, we can calculate the shear stress, right? Very easily based on this equation. Right? And then, so, from the statics, we calculate the characteristic of shear stress, right, of this special case, and we found out shear flow is constant, right? This is a very important characteristic of this case. And then, by integrate that shear flow about the mid curve here, or part of the cross section, we can calculate the twisting moment. And this should be, and then we calculate the relation between twisting moment and stress. Okay, shear stress. Then we need to relate this shear stress with the kinematics, twisting angle, right? Then what should we do? Then we need to calculate the shear strain, right? By using material law. Then we need to calculate the relation between shear strain and twisting, right? Displacement. That's a normal procedure we used before. But today I like to use a little bit different procedure based on energy, because in this case, that energy method is much easier. Okay, let's think this whole shaft and its length is a dx, x, and mx, and twisting angle is d phi, twisting angle. So strain energy. In this case, so externally energy so work, external work. What should be external work? So I gave the moment mx, and this shaft is twisted with angle, this amount of angle. That energy calculated by 1/2 mx d phi. Okay? Twisting angle and moment is energy conjugate. If I multiply both, we can calculate work. Okay? And strain energy. Strain energy equal, this is strain energy stored, and can be calculated by shear stress tau and corresponding strain. So let's say in this case tau 1/2 gamma sx stress Sx T ds dx. This is a strain energy density. Strain energy stored at unit volume. So I need to calculate the volume here. This is strain energy density. Density. And this is volume. Okay. Okay, then for the strain energy, we can use stress Sx equal G material law gamma Sx. Then both externally applied work should be same to the strain energy, right? So 1 over 2 tau square gt ds dx should be same to 1 over 2 mx d phi. Okay, here let's delete 1 over 2 and we divide by both sides with the dx. Then mx dx d phi become g tau square t ds. And in this equation, let's put the result we calculate from the previously we calculate ETA. Then that equation become gt 4t square a square mx square ds. So here m, here mx square, right? So m is a constant. It can be outside of it. And this become mx square gt 4t. So here we have only also t 4gt a square 1 ds. Okay, so if I rearrange that equation, we can calculate final equation dx d phi. This is angle change, rate of angle change, mx, okay, sorry, mx and 4a square g t over 1 ds. This gives us relation between twisting moment and twisting angle, right? So this will give us stiffness, torsional stiffness, right? Relation between twisting angle and twisting moment is a stiffness, torsional stiffness. So dx equal here mx, okay, 4a square g t ds. Okay, this is at the spring, right? Spring force F equal K U, right? U is displacement, F is force, and this is spring. Here, this is displacement, rotation is displacement, M is moment. This is flexibility, right? This is flexibility. Torsional flexibility equal 1 over inverse of torsional stiffness. So, for the circular cross-section case, torsional stiffness was GJ, right? Proportional to GJ. It was GJ. So, here in this case, torsional stiffness equal T over 1 ds 4a square g, right, equal gj, let's say gj equivalent, right? So here we have a g, same g. So we can think this part is equivalent to J equivalent, right? And special case, if T equal constant, dx d pi become 4a square g t s mx. S is a perimeter. You know what's the perimeter? Length of the mid curve. Okay? Length of the mid curve. Example. Maybe most of you think the calculation of this is very hard, right? Okay? Integration of 1 over t ds is very hard to calculate, right? You can think. But I like to show you example, then this is very, you can realize that job is very easy. Let's consider tube. This is tube, scale tube, right? And it has a dimension D, and here B. And thickness, this is thickness T2, and this thickness T1. This is T2, T2, T1. So for left wall and right wall, thickness is T2. For top and bottom wall, thickness is T1. And center of twist is here. This is O. So when twisting moment applied in this section will rotate about the point O, line through the point O. Okay, we are saying this is a center of twist. Calculation of center of twist in this case is very simple, but for general section, it's quite hard job. We need to use some numerical tool to calculate center of twist. Okay. Okay, for that case, let's calculate the this equation. So dx dy equal 4a square g pi t over 1 ds mx. How about a? Calculation of a is very simple. Okay, this is just simply BD, right? BD, very simple. Then how about the calculation of T1 ds? Can you do that? Let's start from here. S is start from here at this point. This is S. Okay? So let from go to here, T will be T1, right? T is a constant from here to here, T1. So T1 over 1 ds. If I integrate this from here to here, that equation becomes like this. Because T is constant, T2. And how about watch this? Huh? Watch this. That is just B. Right? That is just B. Length from here to here. So equation become plus okay, also from here to here, T1 over 1 ds plus something like that, T2 1 ds plus T1 1 ds. This part become D B D. So finally, T over 1 ds become 2 T2b plus T1d, right? Calculation of that integration not very complicated. So finally we can calculate D principal twisting dx dy equal B square, D square, G, and T2 B plus T1 D mx. And this is the same to the 1 of dj equivalent. So now you can calculate the stiffness and stress and strain for circular shaft and arbitrarily shaped closed thin walled shaft, right? So both special cases are just special case. And now we need to talk about general case. Okay? General case is a little bit more complicated. Any question? No? Everything clear? Okay, so let's talk about general shaft, general case. So non-circular shaft, just non-circular shaft. This is really general case. The equation from this can be used for thin-walled cross-section, open cross-section, closed cross-section, even circular cross-section. Okay? So let's consider we have an arbitrary cross-section. And we have here x-axis and mx is applied. So this is mx. Mx is applied. Let's consider this case. Okay, and then let's consider this cross-section. Y-axis, Z-axis, and mx is applied here, mx. And at this some part of this cross-section positioned in Y and X, they are going to be a shear stress, XY, stress, XG, due to the twisting moment MX. Then we can calculate the stress resultant. So, resultant mx equal stress xg y minus stress xy g dA by equal xy dA. by, bg is a shear force, cross-sectional shear force due to the stress x, y, and xg. But in this case, we need to remember that only twisting moment mx is applied. So this is not zero, but this should be zero. Shear force is zero. Okay? Okay, maybe I need to continue the general theory for twisting problem in the next class. Okay, any question?